So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, we will briefly summarize what we did in the recap what we did in the last lecture. So, in the last lecture we started our work on deriving defect concentrations under various ambient conditions. So, we took three regimes of low PO2, high PO2 and intermediate PO2. And we took an example of oxide MO. So, under low partial pressure of oxygen conditions we consider oxygen vacancy as a dominant defect. Under high concentration, high partial pressure of oxygen we consider oxygen interstitials as dominant defects, and oxygen vacancies give rise to electrons and oxygen interstitials give rise to holes. And under intermediate conditions we consider either intrinsic ionization, which is nothing but formation of electrons and holes, or anti-Frenkel defect formation. And this anti-Frenkel defect goes together with the kind of defects that we form in the. So, under low partial pressure of oxygen we have electrons as a result of compensation, electronic compensation. At high PO2 we have holes as a result of electronic compensation due to formation of oxygen interstitials. And anti-Frenkel defects will form because we have VO and OI combination. If you had metal vacancies at high PO2, then we will have Schottky defects. So, accordingly that nature, and we worked out under and limiting conditions of partial pressure of oxygen as well as defect concentrations under so what we worked out was high PO2 and low PO2. So, we saw that under low PO2 condition the partial pressure of oxygen should be smaller than Kr divided by 16 Kr square divided by 16 Kf cube, and in the high PO2 condition we determined PO2 should be higher than 16 Kf cube divided by Ko square. Okay. So, you can see that it is just inverted and that makes sense, you know. And now we need to determine the same thing in the stoichiometric conditions. So, let's first consider so stoichiometric conditions, that is moderate PO2. Okay. So, we consider the case 1 when electron plus hole formation, that is intrinsic ionization, dominates. Okay. So, defect reaction is nothing but this. Okay. We knew that this Ki is equal to Ne into Nh is equal to Ne square or Nh square under these conditions, that is the intermediate PO2. So, basically you can say that Ne is equal to Nh is equal to Ki to the power half, and this is greater than VO or OI. Basically what we are saying is intrinsic ionization dominates. It means there could be Frenkel defect formation, but it is just that concentration of electrons and holes is significantly larger than the concentration of oxygen interstitials or oxygen vacancies formed as a result of anti-Frenkel defects. So, we know that this is Ne and this thing, and we know that VO is equal to, so from the previous reaction we knew that, so we know that VO was equal to Kr divided by PO to the power minus half, PO to the power half into Ne square. Okay. So, now we are not saying that Ne is equal to 2 VO, we are saying that Ne and VO are independent under intermediate PO2 conditions. because Ne is forming through intrinsic ionization, VO is forming through Frankel defect formation. So, they are independent, but this is the relation between the two, how they are related to each other. So, now what you do is that you substitute this expression for Ne, that is Kr divided by Ne to the power Ne square, which so Ne square is equal to nothing but Ki into Po to the power half. So, basically your VO will become in this case oxygen dependent, and this will be VO will be equal to Kr divided by Ki into P to the power minus half. It still has minus sign, but the number has changed. Instead of having minus 1 over 6 dependence, it has minus 1 over 2 dependence. So, this is the expression for VO. Similarly, you can also form the you can also find the expression dependence of so just like we have expression for VO, we had expression for OI. The expression for OI was equal to KO divided by KO. So, we had, so in the previous, just one second. So, this would be equal to KO into KO divided by KI into P to the power plus half. It would remain the same, except that because Ki is now equal to NH square. So, if the you know the reaction was, so from the previous reactions you can see OI would have been equal to, so what is this Ki? Ki is nothing but NH square. Okay. So, it was, so KO was equal to OI into NH square divided by PO2. So, from this we have worked out OI, which is equal to KO into PO to the power half divided by NH square replaced by Ki. So, basically OI is equal to KO divided by Ki into P to the power plus half. So, in case of oxygen vacancies, the relationship goes as minus half. In case of oxygen interstitial, it goes as plus half. So, the instead of plus 1 by 6, we have a case of plus 1 by 2. So, between the two limiting regions, this is how the variation will occur. So, this is in the stoichiometric region. So, within the stoichiometric region, so this is one limiting condition, let us say L1, this is the L2 as a function of PO2. Within this region, Ne is equal to NH. Okay. How will the concentration of oxygen will vary? So, it will cut at some point. So, essentially it will go as minus half in this regime. So, this is VO and plus half in for OI, and then it has to be continuity, it has to follow the continuity in the next regime, and that we will see when we draw them together. So, now you can see what we are going to do using this framework. Second situation, so in the first case, if this is the scenario, when this happens, then we can plot, make a plot of, sorry, let me use the black color. Log of defect concentration as a function of PO2. Okay. I make 3 regimes. This is intermediate, this is high, and this is low. So, this is oxidizing condition on the right, in the middle you have intermediate condition, on the left we have reducing conditions. So, now let us begin with Ne is equal to NH. This is Ne is equal to NH in this regime. Now, since the defect concentrations have to be continuous, the Ne follows this particular sequence with a slope minus 1 over, and Ne was equal to 2 VO, right. And in this case, Ne follows this particular line, which is plus 1 over 6, and Ne being equal to 2 OI, and these are the limiting conditions L1, L2 of partial pressure of oxygen. Now let us make other lines. What about oxygen line? Oxygen line is just half of this. This is VO, oxygen vacancy concentration, sorry, not oxygen line, oxygen vacancy concentration. So this is minus 1 over 6 here. How does it follow in this case? It will go as half. So half means the slope will, it will be something like this, right? So this is minus half, and then again it comes down to minus 1 over 6. Sorry. So again it comes as minus 1 over 6. All right. How about the hole now? How about the so hole concentrations on the other hand, this is the whole line. The whole concentration in this regime goes as plus 1 over 6. This is for NH. Similarly, whole concentration in this regime also goes as plus 1 over 6. What about the oxygen interstitial concentration? Oxygen interstitial in this regime will go half of what we have here. So this is OI, which is half of NH. In this regime the slope decreases, it goes as plus half, and then again in this regime it will go as plus 1 over 6. So this is how the variations of PO2, VO, the variations of defects will occur under different conditions. So under this condition, when the intrinsic ionization dominates, under reducing conditions the dominant defects are these: oxygen vacancies and electrons. Under oxidizing condition, the dominant defects are oxygen interstitials and holes. Under stoichiometric conditions, you are likely to have Ne is equal to NH with lower concentration of OI and VO. Sorry, for VO? Yeah, this is minus 1 over 6. No, this is VO, this is VO. Sorry, Ne, this is minus, sorry, this is minus, this is for Ne. Okay, this should be minus. So is that clear how to construct this diagram? Now let us say the second scenario is, instead of having intrinsic ionization, we make case 2 as, we can say as internal disorder, that is anti-Frenkel defects dominate in moderate PO2s, right. If that happens, then again in the similar fashion we know that Kf is equal to VO into OI, right, which is equal to VO square or OI square, and using the same relation between oxygen interstitial and holes and oxygen vacancy and electrons that we used in previous case, we can determine what is Ne. Ne will work out to be Kr divided by Kr square divided by Kf to the power 1 over 4 into Po to the power minus 1 over 4. NH will be Ko divided by Kf, Ko square divided by Kf to the power 1 over 4 into Po to the power plus 1 by 4. If this is the case, then what we will get is a slightly different situation. In the first case we saw that the slopes were of some type, in this case we will have slopes of another type. So again we make this line log of defect concentration PO2, again we make 3 regimes. So this is high, intermediate, low. In the intermediate regime we can say now instead of NE being equal to OH, we have VO being equal to OI. So, VO will follow the same line. So, VO will follow this line with a slope minus 1 over 6, and this will go as minus 1 over 6 in this region. This is VO. For OI, it will follow this line plus 1 over 6 and minus 1 over 6. NE and NH on the other hand will be now different. So, for NE, this is NE, but so it will, so this is NE and slope is minus 1 over 6. In the now from the previous equation you see that now it has to follow a slope of minus 1 over 4. So, it will follow a slope of minus 1 over 4, minus 1 over 4, and then again it will follow a slope of minus 1 over 6. Similarly, holes, for holes this will be for holes NH, same slope, and now it will reduce its slope to plus 1 by 4, and before it takes a slope of plus 1 by, sorry, this is plus 1 by 6. So, they will have slopes of plus and minus as per their character, but now the behavior has changed thus. Okay. So, this is basically the way in which you construct what we call as a Brewer's diagram, the diagram which provides you a plot of defect concentrations of all types as a function of partial pressure of oxygen at a constant. So, this is at a constant temperature, okay, constant temperature, and this is also at T is equal to constant. And mind you, this is also valid for a given oxide MO, considering that defects are VO and OI. If you have MO2, what will happen? The slopes will change, the partial pressure of oxygen dependencies will change, and the boundary conditions L1, L2 will also change. Okay. So, when you change the type of defect, when you change the type of oxide, the slopes will change, the limiting conditions will change, but the procedure will remain the same. Okay. So, procedure to calculate this is basically first, so when you want to know how to construct a Brewer's diagram, so what are the steps? First, you need to see the relevant defects and type of material, right. So, you need to see what kind of defects can be present in the material. Basically, there are 4 possible defects which are possible. You can have oxygen interstitials, oxygen vacancies, metal interstitials, metal vacancies. You need to know the defect formation energy, and depending upon the type of oxide, those with the lower defect formation energies are more likely to form. So, when you identify the type of defects, so identify relevant defects and type in a type of material, okay, and then write the defect reactions. Okay. So, generally for a close packed structure, you know, one can neglect interstitials. If the structure is very heavily close packed, then interstitials are not possible to occur, because interstices are not, they are smaller, and generally oxygen interstitials are bigger. So, as a result anti-Frenkels will not be possible. So, for such kind of materials which are close packed structured material, you will mainly consider what we call as Schottky disorder, not anti-Frenkel or Frenkel disorder. So, that judgment has to be made by you as a scientist, and then once you identify the defects and type of defects, intrinsic defects, etc., you write the defect reactions. So, once you write the defect reactions, you work out the dependence of defect reactions and reaction constants, okay, and work out the dependence of defect concentration on PO2. So, you do it for low PO2, do it for high PO2 and do it for moderate PO2. When you do it for moderate PO2s, then you also have a situation whether you may have intrinsic ionization dominant cases or you may have internal disorder, right, in terms of Schottky or internal defects such as Schottky or Frenkel. Okay. This depends generally on the band gap. If band gap is low, then intrinsic ionization is favored, but if your band gap is so you have to consider the energies in terms of EV per defect or whatever, which ones are lower. So, if your defects can be formed easily, then internal ionization will occur less, and if your internal ionization can occur at lower band gaps, then defects will be difficult to form. So, and once you do that, then you basically find out what is the limiting conditions, right. Limiting conditions will give you boundaries of PO2, right. So, basically if you have n defects, you will have n minus 1 equations that you may have in the system. Okay. And so, you define these regions of PO2, define PO2 regimes, and then you have to use your logic, then logically draw the concentrations, making sure they are continuous, they do not become discontinuous as you go switch from one to another region. So, as we saw in previous figures, you look at electron concentration or hole concentration, or you look at oxygen vacancy concentration, or you look at oxygen interstitial concentration. No matter what the situation is, the defect concentration remain continuous. It is just that their slope changes as a function of partial pressure of oxygen. So, these diagrams are very useful, and these diagrams allow you to understand what kind of defects can be present in different systems as a partial pressure of oxygen. And now I can just briefly tell you about how much is the, so when we work out the extent of non-stoichiometry in these oxides. So, the question is oxides can be non-stoichiometric. So, how much non-stoichiometric can be? So, let us see a brief discussion on non-stoichiometry extent. So, in materials like MgO or alumina or even zirconium oxide, the extent of non-stoichiometry is small. They are generally very stoichiometric oxides because the energy which is required for oxidation or reduction is very large. So, as a result, the defect formation energy is very large, and as a result change in partial pressure of oxygen has little effect on the defect chemistry. So, small changes occur as PO2 change. So, these are very robust systems, they have large defect formation energy, and the cations also they are generally of, so magnesium generally occurs in only +2, aluminum is most stable as +3, zirconium is also very stable as +4, they do not have valence fluctuations. So, lack of valence fluctuations makes them very stable oxides. So, extent of stoichiometry is very small in these systems. So, basically you can say they have large defect formation energy. So, energetics does not permit them to be non-stoichiometric. On the other hand, elements such as TiO2 or barium titanate or even strontium titanate, iron oxide, they are all very, so these are defect containing oxides, because the defect formation energy in these defects in these oxides is very small, in these smaller, relatively smaller. So, you can form in these systems oxygen vacancies, you can also form valence fluctuations, and so on and so forth. So, as a result, these systems where you have transition elements, especially Fe3O4, you can have Mn3O4, you can have MnO2, things like tungsten oxide, molybdenum oxides, bismuth ferrite. All these systems they are prone to having valence fluctuations and oxygen vacancies, especially in the system, and hence titanium can occur in Ti+3 state, for example. Okay, if you have Ti+3, then oxygen content will go down. Similarly, in this oxygen content will go down. Similarly, in strontium titanate oxygen content may go down. So, because of valence fluctuations, you may have non-stoichiometry, and as a result, so similarly, if you look at oxides such as NiO, FeO, MnO, cobalt oxide, all of them are prone to having reasonably large defect concentration, because Ni can be, it is a transition metal ion, Fe is transition metal, Mn is transition metal, cobalt is transition metal. So, Ni can occur in different valences, Fe can occur in different valences, manganese can. So, this brings non-stoichiometry in these systems. So, they can again have a non-stoichiometry of about 0.05%. 0.05% is very large. Okay, 0.05%, it sounds a small number, but on a, when you have about 20 something atoms in a system, 0.05% is very large number. So, and here we are stoichiometries of the order of few ppm, or few ppm non-stoichiometry is good enough to give you large defect concentration. So, stoichiometries occur. So, these are non-stoichiometry prone materials, whereas on top we have materials which are stoichiometry, they are generally resistant. So, this is what it is, and we have seen how the defect concentration varies as a function of partial pressure of oxygen. So, this sort of gives you an idea what you can do with oxides. If you wanted to make them oxygen rich, then you can use conditions to anneal or calcine in such a condition, so that they become oxygen vacancy rich or metal vacancy rich. So, and you can dope them with certain impurities to tailor their defect concentration. So, if you wanted to make something lower in, let us say, BaTiO3, if it is oxygen deficient to begin with due to titanium oxygen valence fluctuation, you can dope it with something like niobium, which brings in extra oxygen into the system. So, this is how you make oxides conducting or non-conducting by using the defect chemistry. So, this knowledge is very important to engineer because the defect concentration is directly proportional to conductivity. So, defect concentration is proportional to conductivity. So, as defect concentration goes up, generally that conductivity also goes up, and for dielectrics we need to reduce the conductivity. So, we need to reduce the defect concentration either by calcining them in conditions or sintering them in conditions which reduces the defect concentration, or if you cannot achieve that, then you need to dope it with appropriate dopants, so that you reduce the defect concentration which has been prevailing in that material. Okay. So, for example, as I said, barium titanate, titanium is prone to Ti3 plus formation. So, as a result it becomes BaTiO3 minus delta, which means it will have oxygen vacancies in the system. So, if it has oxygen vacancies in the system, then I bring in niobium oxide. If I bring in niobium oxide, then niobium goes to titanium site. So, 2 niobiums go to titanium site, 5 oxygens go to oxygen site. So, 2 of them are related to titanium, 4 of them are related to titanium, and 1 of them is related to VO. So, as a result they sort of compensate. So, in charge compensation is done by like this. So, your oxygen vacancies are compensated by these extra oxygens brought in by the +5 valence. So, that is how you make it resistant to conduction, and this is very important in the context of dielectric materials. Dielectric should be insulating, that is why you need to control their defect chemistry very accurately, and this knowledge hopefully will enable you to do that. Okay. So, let us stop there. So, this completes our discussion on defect chemistry. From the next lecture we will start discussion on dielectric ceramics, starting with linear dielectric materials. Thank you.